In this video, we look at the method for deriving state space models from ordinary differential equations. A state space model describes the first-order derivatives of the state variables. In many systems, the state derivatives depend not only on the current state, but also on an input. An input might be an applied force, an applied torque, or a voltage from a controller. When we include an input, the general state space form becomes x dot equals f of x u. This means that the state derivatives can depend on both the state x and the input u. For a linear system, this becomes x dot equals ax plus bu. The ax term describes the state-dependent part of the dynamics. The bu term describes how the input enters the dynamics. The rest of this video gives a recipe for deriving the state space form from an ODE. In this example, we start with the familiar mass spring damper type equation, now with an input u. The equation is second order because the highest derivative is the acceleration q double dot. But state space form uses first order ODEs. So our job is to rewrite this one second order equation as two first order equations. Because the original ODE is second order, we choose two state variables, x1 equals q and x2 equals q dot. The first state equation comes directly from the definition. Since x1 is position and x2 is velocity, the derivative of x1 is x2. For the second state equation, the derivative of x2 is acceleration q double dot. Because x2 dot equals q double dot, we isolate q double dot from the original ODE. Then we replace q with x1 and q dot with x2. This gives the final first order equations. x1 dot equals x2 and x2 dot equals minus k on m times x1 minus c on m x2 plus u divided by m. Now, the original second-order ODE with input has been rewritten as a system of two first-order ODEs. On the previous slide, we rewrote the second-order ODE with input as two first-order equations. Now, we collect those two equations into vector form. The left-hand side is the derivative of the state vector x dot. The right-hand side lists the expressions for the two state derivatives, including the term involving the input. This is already a state space model. In general, we can write it as x dot equals f of x u because the state derivatives depend on the state variables and the input. In this example, the equations are linear in the states and the input. So we can also write the model in matrix form as x dot equals ax plus bu. The A matrix contains the coefficients multiplying the state variables. The B matrix contains the coefficients multiplying the input. Here, the input does not appear in the first state equation, so the first entry of B is 0. The input appears as u divided by m in the second state equation, so the second entry of B is 1 on m. The same conversion method works for higher order ODEs. For example, suppose we have a third order ODE with input u. The equation is third order because the highest derivative is q triple dot. So we need three state variables. A standard choice is x1 equals q, x2 equals q dot, and x3 equals q double dot. The first two state equations come directly from these definitions. x1 dot equals x2 and x2 dot equals x3. For the third state, x3 is q double dot. So x3 dot is q triple dot. We isolate q triple dot from the original ODE, then replace q, q dot, and q double dot with the state variables. This gives x3 dot equals minus a naught x1, minus a1 x2, minus a2 x3 plus u. So a third order ODE becomes a system of three first order ODEs. Let's finish by summarizing the conversion recipe. For a single higher order ODE, first choose the state variables. The standard choice is the original variable, then its first derivative, then its second derivative, and so on. Second, differentiate the state variables. The lower order derivatives follow directly from the definitions. Third, use the original ODE to replace the highest derivative. This is a step where the original dynamics enter the state space model. Fourth, substitute the state variables so that the final equations are written in terms of the state variables and the input. This gives the general state space form x dot equals f of xu. If the equations are linear, we can also write the model in matrix form as x dot equals ax plus bu.